Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on October 16, 2025, about 3 days ago. The standout result is a scheduler called Seesaw that matches cosine decay in loss versus compute, while cutting wall clock training time by approximately 36%, approaching the theoretical limit of 36.3%. The paper is titled, Seesaw, Accelerating Training by Balancing Learning Rate and Batch Size Scheduling, and the implications for model training are quite significant. In short, this paper formalizes batch ramps, proves an equivalence between learning rate cuts and batch size increases, extends it to a normalized atom proxy, and demonstrates robust speedups at Chinchilla scale. Alright, the previous intro set up the idea of trading learning rate cuts for batch size increases. Figure 1 shows 6 panels comparing cosine, solid lines, and seesaw, dotted lines, for 150 million, 300 million, and 600 million models. The top row plots validation loss versus tokens, so compute, and the curves overlap closely, which means matched loss dynamics. The bottom row plots loss versus steps, and the dotted curves shift left, indicating faster wall clock by roughly 1/3. So the previous figure showed matched loss with faster steps for Seesaw. Algorithm 1 presents Seesaw, a simple scheduler that takes an initial learning rate, an initial batch size, a decay factor alpha, the cut steps S, and total steps. At each cut step, the learning rate is divided by square root alpha, and the batch size is multiplied by alpha, which preserves loss dynamics while reducing serial steps. The design assumes a variance-dominated regime, so larger batches mainly reduce noise rather than change the optimization path. Well, Algorithm 1 explained how the scheduler trades learning rate cuts for batch size increases. Table 1 reports final validation losses for 150 million, 300 million, and 600 million models across batch sizes 128 to 1024, comparing cosine with Seesaw. The numbers are nearly identical, differing by only a few thousandths, with 600 million missing at batch 128. This consistency at the critical batch size supports matched loss dynamics while enabling faster training. Okay, the previous table confirmed matched final losses across sizes. Figure 2 compares validation loss at batch 256 and 512 for several alpha and beta pairs that lie on the equivalence line, where alpha times square root beta equals 2. The blue curve, alpha 2 and beta 1, serves as the target. The red and purple schedules deviate, which aligns with the stability limits, so those aggressive choices underperform. The green and orange traces track the blue curve closely at both batch sizes. So the previous figure tested stability along the equivalence line. Figure 3 shows what happens past the critical batch size. Cosine in blue continues to drop, while Seesaw in green and a fixed learning rate ramp in orange lag behind, and the gap widens with larger batches. The top left panel at batch 1024 stays close, but the top right at 2048 begins to drift. The bottom panels at 4096 and 8192 reveal clear underperformance, which signals that the variance-dominated assumption breaks at these scales. So the previous figure showed breakdowns beyond the critical batch size. Figure 5 compares 4 schedules at batch 128 on the left, and at the critical batch size 256 on the right, plotting validation loss versus tokens. The green baseline that halves learning rate at fixed batch size, and the red seesaw trace overlap closely, which indicates matched loss dynamics. The blue curve with fixed learning rate and double batch size lags behind, and the orange quadruple batch setting also trails, especially at the critical batch size. Alright, 2 takeaways stand out. Seesaw preserves loss dynamics while cutting wall clock by about 36%, and it gives a principled rule for batch ramps instead of guesswork. The broader implication is practical, a drop-in scheduler that saves time and cost up to the critical batch size. Thanks for listening. I am Alex, and this was the AI Research Roundup.